so we're linked to both IMO and the ML department here at Moffitt. So Russ is a applied mathematician who got his degree in applied mathematics at the University of Colorado. Went on to do a PhD with you, obviously, that would be quite weird.
Yeah, right.
Although, you're qualified to supervise students now. So with a time machine, with Kristen Swanson, so a PhD at the University of Washington, and then went to do a postdoc also with Kristen Swanson at Northwestern, and then started his own, I was going to say group division as well, right? He leads a division, he's the director of the Division of Mathematical Oncology at City of Hope in California. A division that has started from a very small group of people that now has a number of faculty and is well funded by NCI grants from CSBC and PSON. And clearly your interests are going to include not only mathematical oncology, but also machine learning. So I'm looking forward to what your presentation is about today.
Yeah, thanks. Thank you, David. Thanks. I'm really, really happy to be here. I haven't actually, so I gave a virtual seminar last year, but I haven't actually given an in-person one. Although the first time I came here was before the Collaboratorium was built, I think in 2006, maybe.
We weren't even in this building.
Right, exactly, in the temporary building. So I'm definitely very, very happy to be here. And thanks, David, for that nice introduction. But also, I did want to talk about something that I felt like might be of interest to both departments. Okay, it's something that I'm also very excited about right now. So, I'm very curious to hear all your thoughts about this talk. Okay, machine learning biology. Okay. So the motivation for all of this work really comes from this person here, Christine Brown. She's a biologist, a CAR T-cell biologist, which I'll tell you about in a minute. But when I came to City of Hope, she really wanted to see what we could learn through mathematical modeling about how her CAR T-cells were working or not working. And so, the fundamental driving question of, what are the predator-prey-like interactions between the effector, T-cells and the target cells was kind of something that we've been working on in various different ways over the last 5 or 6 years or so. It's really this nice integrated group of people collaborating together, biology, math, experimental biology, physics, and engineering. And so I'm excited to tell you just a small piece of what we've been working on in that space. So Christine Brown is one of the leaders in the field of chimeric antigen receptor T-cell immunotherapy, which I probably don't need to explain very much to any of you, but I'll have this one slide just in the small chance that maybe somebody online isn't familiar. But the idea here is that it's a type of immunotherapy for cancer where you take the T-cells out of the patient's body and then you re-engineer them to be specific to a target through a chimeric antigen kind of gene construct is what it's called. And then you expand the T cells in vitro and then you put them back into the patient with the idea that now the body's immune system has been trained to be targeted towards that specific target on the cancer. Okay. And in particular, Christine's work is focused on glioblastoma, although our work in this area also applies to CAR T cells in multiple myeloma and in prostate and many other applications. But Christine's really a leader in glioblastoma, which is a primary brain tumor, which also probably you are very familiar with because I know one of the teams in the workshop this year was working on GBM. But just a very high level summary and this picture up here. This is part of the reason why I'm in town, although not the only reason for sure. I wish I could just spend all my time here, honestly, is the Society for Neuro-Oncology, which is the annual brain tumor meeting, is being held here starting tomorrow, like David said. And glioblastoma is the most common primary brain tumor in adults, very highly aggressive, very short overall median survival. And there really hasn't been any meaningful progress in treatment of this cancer for like 15 years. And so new treatments or improvements in existing treatments really, really are desperately needed. And so City of Hope is, I would say, very world-renowned, in fact, for writing this paper in the New England Journal of Medicine a few years ago now, showing arguably the first ever complete remission of glioblastoma in a patient, and it was the result of these CAR T cells, and it really catalyzed this entire field of work of applying CAR T cells to solid tumors because they had shown to be effective in hematologic and liquid cancers. So this is really one of our kind of claims to fame. We study this patient a lot, this particular patient, but has motivated a number of clinical trials. So there are these 4 clinical trials, at least over 100 patients at City of Hope in glioblastoma aim to be treated with CAR T cells targeting for a number of different targets, a number of different routes of delivery. And so that's very unique. In fact, City of Hope's probably one of the top 3 leading institutions in the world for a number of CAR T cell clinical trials for brain tumors. And I just wanted to make a note here, particularly for this audience, is what's really nice about where I'm at, and I know you guys share this here at Moffitt too, is, I'm actually really integrally involved in the clinical trial design. So if you go on clinicaltrials.gov for any of these trials, you will see as a secondary endpoint, pre-designed secondary endpoint in the clinical trial, either a mathematical model analysis, like a tumor growth rate analysis, or an imaging endpoint, something that I'm not going to talk about too much imaging stuff here today, but really, really they're wanting to think about how can we integrate mathematical modeling, mathematical thinking into this kind of therapy. And it's really, really awesome to work on. So that leads to this question, right? How can mathematical oncology help improve CAR T-cell immunotherapy for glioblastoma? Big question. I'm going to show you how we're working in it in very small ways, but actually, what I want to talk about today is what I'm excited about on the math and modeling side. There are other things that I think are probably less exciting for this audience that I do work on, which is more on the imaging side. Ryan and I do a lot of stuff on the imaging side, imaging kind of analysis, but I want to talk about a modeling approach that we're doing that I hope will be translational. And I put this in here mostly for Kim Luddy, okay, my favorite immunologist. So I'm going to start talking about immunotherapy. So you have to promise not to shoot me, okay? You might remember this Atlantic piece from who, before he won the Pulitzer Prize, Ed Kim wrote that immunology is where intuition goes to die. And he has this great joke that starts it, okay? It's an immunologist and a cardiologist are kidnapped. The kidnappers threaten to shoot one of them, but promise to spare whoever has made the greater contribution to humanity. The cardiologist says, well, I've identified drugs that have saved the lives of millions of people. Impress the kidnappers, turn to the immunologist. What have you done? He asks. The immunologist says, the thing is, the immune system is very complicated. And the cardiologist says, oh, just shoot me now. Okay? Because anybody who's worked with an immunologist knows that this is basically how every conversation goes. It's complicated, okay? I'm going to give a warning here, the spherical cow kind of mathematical warning. This is a drastic oversimplification of something that is obviously extremely complicated, okay? But it's just how we're starting to think about a lot of this stuff. So I tried to find a good picture of a turkey for this, but I couldn't. Chicken and the egg. What comes first, the data or the theory? It's actually something that we've started to think a lot about in my group and at City of Hope. And like the chicken and the egg question, there isn't really an answer. Okay, they're both there. Maybe one's there first, maybe the other's there first. Really, kind of no great answer. Okay. But when we think about mathematical modeling, I hope we all know that it's an art. And so one important fact that David missed in his otherwise great introduction for me was that I also have a degree in art. So my undergraduate degree is in mathematics and art. I tried actually to make it as an artist and failed. And so I decided to do math. But anybody who's written down mathematical models like we have in this room, know that, they can range from something that's incredibly detailed to something that's very simple. And I hope that some of you recognize this drawing on the right as being a self-portrait from John Lennon, okay? It's extremely simple. And once you know who it is, you recognize it immediately. So it captures all the kind of essential features. But usually this is how modeling ends up going, right? And this is like, okay, you start with really great intentions and then you have to end up making all these kind of ridiculous approximations in the end and you end up with. But so how does mechanistic modeling and,
I was about to say, I don't consider you a failed artist because I have one of your masterpieces in my office.
I appreciate that, Sandy. Well, I will say as a career. As a career.
Still dabble?
Yeah. In fact, now that my kids start to get really into art, I've been doing more. In fact, I did some watercolors with my dad a couple weeks ago. I'll show you.
Nice.
Yeah.
So Sandy, the question is how much did you pay for it for him to be successful?
I don't think I paid anything.
No, I paid him to take it. And I said, here it is, and here's money to frame it, and I better see it next time I come to Iowa. So how does modeling and machine learning come together? And this is what I really want to talk about today. It's going to take a little while to get there, but we're going to build up to it, because you all here know how modeling basically works. It's like you have an idea, you have an experiment or an observation, you get some data, and ultimately what you have to do is take an educated guess at the equations, right? You have to basically kind of, I don't know, it's a product, it's a Hill function, it's something like that. And then you have to check your equations with the data, and on it goes. And if you get it right, you're in the pantheon of scientific achievement, right? I mean, if you get a lot of equations right, like Einstein, like many other people, I mean, this is a very, very significant contribution, right? But it involves a lot of educated guess and check. So what if you didn't have to do that step? Okay, that's what I'm going to talk about today. What if there was a machine that could learn the biology, and there is that possibility? That's what I'm going to show you, okay? It's called, and I'll say this over and over today, SINDI, okay? Sparse identification and nonlinear dynamics, okay? And this is what I hope to be a seminal paper in all of your literature going forward after this talk anyway. It's a 2016 paper published in PNAS, actually from my old department chair at the University of Washington, Nathan Coots, and another junior faculty, Steve Brunton, who's now more senior faculty. And the idea here is that if you have enough data, and this is the catch, but I'll show you in some cases we can. If you have enough data, what you can do is you can, instead of doing a regression to match the data with the model, which we usually do, you fit the model to the data, right? Instead of doing a regression in data space, you do a regression in function space. You regress in the library of functions of candidate terms that could construct your model. So this is a figure from their paper. You take the Lorenz system, which you may or may not know, but very, very famous one, XYZ three-dimensional model that exhibits chaotic dynamics. And what you do is, in this particular simulated case, run the model forward. You create this big vector of derivatives with respect to time, x, t, y, t, z, t. And then you put in this library matrix, theta, the terms you think are in the model. And here's what's really important. What terms do you put in that library is up to you. You can put all kinds of stuff in there. Hold on to that thought, okay? And then you have this coefficients or weights matrix here, C, and then and if you build this library sufficiently large, then you can take advantage of the sparsity of that matrix. And when you solve this matrix equation, you can actually come out and identify the underlying equations that generated that data. And that should feel like absolute magic to you. If you don't know this method already, I hope that you're wondering how the hell this could possibly work. But it does, and they have multiple papers on it. It's spanned across the globe, multiple different groups reproduced it. It works, okay? It will find the model in all kinds of systems. The model that's put in. Yeah. So the model, in this case, it's the Lorenz model. They've also showed it in the Navier-Stokes model.
I presume it will find many compatible models. It
could find many compatible models, and that is something that we are going to talk about. What are other examples, Ryan, they've done? So Lorenz, Navier-Stokes, Erger's equation, all the famous applied mathematics equations. You run them forward, and then you can identify. Yeah.
Hey, Russ, I haven't seen that, so I'm really excited what's going to happen next, and you're probably going to talk about, but have they added noise?
I am actually not going to talk about noise today, but they have. And in fact, there's a whole class of SINDI methods to deal with noisy data that we use. But I'm not going to talk about today.
So cool. We talk about later.
Yeah, we talk about in this room after or whatever, but yeah, I don't have any slides on that today, but yeah. Okay, so what's great here about SINDI? It's really at the intersection of physics, biology, your knowledge, machine learning, and the data, okay? So like I had that slide before, it eliminates this step that we all face, which is oh, well, what is the model? What are the terms? Okay. So this is a really cool, beautiful movie. It's in Quanta magazine. I know a lot of you are on Twitter, so probably you see Quanta tweets and stuff like that. But this, if you're not familiar with Quanta magazine, I suggest you read it. You'll love it. They write all kinds of really great stuff. What this is a simulation that was done by some group at NASA, where on the left they took trajectories of planetary motion and they trained a machine learning model on it, okay? And on the right, what they did is they did the Cindy version. So they did the Cindy-based machine learning where they regressed and derived Kepler's planetary laws of motion and then ran the identified equations forward in time. And what you see is that the machine learning model on the left starts to diverge over long periods of time. And that makes a lot of sense, right? Because small variations in the trajectory, maybe you don't have complete trajectories to learn on, all kinds of things. It starts to deviate over long periods of time. Whereas if you use the underlying governing equation and you solve the governing equation, it predicts the planetary motion in a much more stable, much more long-term way. Okay, and I thought this was just like a particularly beautiful way to illustrate this. So what comes first? Well, like I said, I structured this talk in a very specific way. Okay, so let's go with the model first approach first. Let's go with the egg, so to speak, first. Okay, so let me show you what we did before Cindy made me lose sleep. Okay, which I literally lost sleep after I read that paper. So the first paper I'm going to talk about is one that's a couple of years old now. Driven by postdoc Prativa Sahu. She was actually my first postdoc here in the Journal of Royal Society Interface. Title is Mathematical Deconvolution of CAR T-Cell Proliferation and Exhaustion from Real-Time Killing Assay Data. Because we like good long titles, right? But it does tell you exactly what it's about. Like we all know, and I just found out from Ola, she has a good acronym here for her department seminar, Emerge. We had a great name for the model. It's CARGO. CAR T-cell response in glioblastoma, okay, a predator-prey model. And what is this? This is what we all would expect to do. We have CAR T-cells, they're predator. We have tumor cells, they're the prey. And you write down something like we're kind of all used to seeing, some logistic growth in CAR T-cells, and then the CAR T-cells and tumor cells kill each other, or the T-cells kill the CAR T-cells, and then something else happens and they die. And this is a very nice old model, but we chose it because it had a lot of properties that we really liked. In particular, you can have successful CAR T-cell treatment where, depending on how many cancer cells and how many CAR T-cells you have initially, you can have a transient progression before eventual response, okay? Or you could just have a rapid response. Or in the case of CAR T-cell treatment failure, you could have a pseudo response where it actually appears to respond and then eventually fails. These are features that we really like because these are things that we see in preclinical mouse experiments, in the human data. And so we're like, okay, well, this is the John Lennon style model where we think, okay, it's captured all the essential elements, let's use that, okay? In particular, it was designed to capture known biology, be structurally identifiable with the data available, which is really important, right? I know that Heiko thinks a lot about this. I know a lot of us do, but I mean, like, there's just enough parameters in here that we could actually calculate them and estimate them all from the data that we had. And we were very happy with that. So what did we do with it? We did a highly simplified experimental system, and this is me just fending off Kim getting too upset about it. But this is an extremely simplified system, okay? It's called an excelligence assay, where you have this 96 well plate and the machine reads changes in electrical impedance. So the cells adhere to the bottom of the plate. It takes about a day for them to adhere to the bottom of the plate. Then you put in some CAR T cells and then you watch the dynamics play out through changes in the impedance. And that has a readout here called cell index. And here what you see is, for example, the tumor cells in red and kind of the CAR T cells, wait a minute, in yellow. And the amazing thing about this assay or this experimental system is that it measures almost continuously. This is data. This isn't a fit. The data is measured like every 15 minutes. So, I mean, that shows you that this is actually a real continuous, smoothly varying system, okay? It's actually, when they showed me that they had this system, I was like, oh my God, we at least have to do something with this, okay? And just in case you were wondering, yes, the readout of impedance is correlated with the number of cells. So this is a paper that was published in 2006 when this machine was invented. Pretty sparse data points, but showing a very, very high correlation, which we reproduced in our cell lines, by the way. So definitely changes in impedance correlated with cell number in case you're wondering. And this is kind of a modeling side note, but like I said, I'm kind of building up here for a specific reason. When I started looking at these curves coming out of this machine, I noticed something. And you see here at the beginning how the curve is concave down, right? Graph curve, the growth curve's like that, starts like that. Not usually like that. right? Exponentials like that, logistics like that, it's also kind of like that. It's not very often concave down. It just happens to be that I studied this equation with Kristen for like 10 years, which is a reaction diffusion equation. I just happen to instantly recognize that how do you get a tumor growth curve that is concave down initially is with the spatial component. So if you write down a PDE with a diffusion, a simple diffusion and logistic reaction, actually you get now here's a model data fit right here. And you just don't get better than that, right? I mean, it's one of those like, oh my God, I can't believe it works like that. I mean, really, really capturing exactly what's going on in that well. But that's kind of an aside. So we did all kinds of things that you would want to do in a model first approach. We looked at, how stable were the model parameter estimates, depending on how much data we use. So if you downsample the data half, or by a fourth, do you still get the same parameters? And you do. Okay, so it's good. It's a good, stable, nice, identifiable model. And then we applied it to a couple of different cell lines. So this is a patient-derived cell line here. This is an immortalized fibrosarcoma cell line, something like that. And then we fit the model to the data, as you do, okay? And it was just amazing how well it fit. I mean, I just couldn't believe it. I was telling Prativa, it's like, just take a good mental snapshot of that because I don't think you get to see it that often. Mm-hmm. So, plotting the trajectories in the phase space, they go exactly where you'd expect them to, even in time. And the model fits the data perfectly. And you start to get some interesting kind of insights, which is why you do modeling. And that is that the CAR T cell killing rate is actually inversely proportional to the effector target ratio. Why? Because the more CAR T cells you put in there, the less fast they have to kill. That's something that to people in this room probably makes a lot of sense. I promise you it took a very long time to explain to the biologists, okay? But that's something that we got out of that model. We also looked at how these results depended on the antigen expression. So these CAR T cells were targeted for a very specific antigen. So we took the cell line with all these different levels of antigen expression and did the modeling across these two different cell lines and saw these nonlinear dynamics that honestly were kind of hard to make sense of because the CAR T cell killing rate was very non-linearly related to antigen number of antigen positive cells, and so was what we called the exhaustion rate. And so that was an interesting insight that then we were like, okay, we'll go through and validate that.
What does it mean to be negative then? Is that just a parameter?
Very good question. Okay, so kappa 2, I wasn't going to spend too much time on this because I want to get to the Cindy part, but kappa 2, we don't actually enforce any sign on kappa 2, so it's the interaction between the CAR T cells and the tumor cells. So if it's negative, it's actually impeding the CAR T cell, population, which also is some biological known fact, right? So it's like they can actually start to deactivate the T cells under certain high densities, right? So negative means that it's actually inhibiting the T cell population. And then we did this other thing where we correlated the killing with the proliferation and didn't see any correlation, which is one you might expect. But we did see a correlation with this K2, kappa 2 parameter that Sandy just asked about, which is okay, higher the tumor proliferation, the more the T cells get exhausted. And that was very interesting, and that was very cool. And then we applied it to that very famous patient from the New England Journal who had multiple lesions, and we fit the model to that patient's imaging data and found that, oh, look, the lesion that didn't respond had a higher tumor proliferation rate. So this was by all measure, a really great piece of mathematical biology that I remain very, very proud of, okay? But it was a very model-first approach.
Can I just ask briefly, I know you don't want to discuss it, but are you just summing up the tumor burden there volumetrically? Or
each lesion tumor volume burden, that's right, yeah. And the big limitation with this analysis, which we considered not even putting in the paper, but we did anyway, is because you can't really know how many CAR T cells got there. So you have to make some kind of estimations.
Proportional to volume or?
Yeah, proportional volume, exactly right. Yeah. But it worked, so we were happy. And so then we said, okay, well, we got a lot of mileage out of cargo. Let's ask another clinically relevant question, and that is, what happens with dexamethasone? Dexamethasone is an anti-inflammatory immunosuppressant steroid that brain tumor patients get to help with swelling that's induced in their brain. And they almost always get this but because it has immunosuppressant effects, it's very unclear whether or not this would be beneficial or not for CAR T cells. Okay, I don't have to if anybody's really interested, I can think through that with you right now, but basically the basic idea is it's very unintuitive how that should actually work out. So Alex Brummer, who was the first author of this paper and also the first author of the Cindy paper, who I think is online right now, he was a postdoc with me doing this work, but now is a faculty at College of Charleston, just north of us here on this other coast. And and this is the PLOSCOM bio paper I just want to show you about. So it's show you. It's the same Excelligent system, so it's still this 96 well plate kind of system, and the cells
At the West Coast.
the best.
I like how you go wrong.
Sorry. You should know better. And so the tumor cells adhere to the bottom. And now, instead of putting just CAR T cells in, now we put CAR T cells in varying levels of this corticosteroid dexamethasone. So the question was, how does this affect the dynamics? Here's just what some of the data looks like for your interest. And here's this kind of schematic of the model, but here are the equations. And so again, in a model-based first approach, we took something that was I would say maybe a little self-indulgent here. And that is said, okay, well, let's add to the cargo model the dexamethasone. And it's just a decaying concentration. Because remember, this isn't a body, this is a well. So the dex gets put in the well and it basically just, gets absorbed into the media or eaten up by the cells and it just basically decays away. And that would be an autonomous model. But we decided to play around with it in a kind of cool way and make a non-autonomous model. So we just solve the D equation for concentration and then plug that directly into the cargo model. Just to see, now that you have T explicitly on the right-hand side, what does that do? Does that help anything? And I'll tell you real quick that we didn't a priori assume any interaction between DEX and the tumor or CAR T cell population. We didn't enforce a sign for these coefficients C0 or C3, okay? So why do a non-autonomous model? Besides, like I said, a little bit of self-indulgence to say, oh, well, it's interesting to do. Have you done that before? No, let's do it. Well, it turns out that you can analytically solve it. Yeah.
So I'm still a bit hung up about terminology. So non-autonomous just means you solved explicitly for the DEX concentration?
No, non-autonomous means that there's T explicitly in the right-hand side. It means that you have something like X dot equals a function of X and of T, not F of X of T.
Thank you.
Yeah. I do love grabbing a piece of chocolate.
Here for you.
Yeah.
Thank you. So it has another advantage, and that is that you can actually solve the equations explicitly, and then you can explicitly mathematically study the dynamics of the behavior, which is, appealing from a mathematical point of view. So we can kind of group the terms into, what they're doing to the solutions. This term in here under the square root is determining the oscillatory behavior, whether or not there's imaginary complex roots. And then the sign out here in front kind of determines whether or not they're stable. And that ended up being very interesting and cool in a model first approach, right? Because you can draw these dynamic phase spaces. Now the phase space now changes in time. And you can really look at what that dexamethasone perturbation does to the system dynamics. And that was intrinsically very cool from a mathematical point of view. And then what we did is we fit the model to data, a number of different cell lines and a number of different dexamethasone concentrations, looked at the parameters. And remember, I told you that we didn't specify whether C0 or C3 were positive or negative. So what we started to see was that in some situations, dexamethasone could actually be stimulatory. Sometimes it could be inhibitory to various degrees. And so, very, very cool, interesting stuff that basically summarized into each tumor cell line that we studied at different effector target ratios or T cell to tumor cell ratios had different kinds of thresholds at which dexamethasone was either inhibitory or allowing the tumor to progress. And so that was also very helpful from some sense, from the clinical sense, because maybe once you say it out loud, maybe it feels very obvious that it's cell line dependent and dose dependent, but until you kind of really mathematically show it, it's maybe not totally convincing. So we said, okay, well then we should really study the dexamethasone concentrations in the patients and on these clinical studies, which is something that we are doing. But, okay, finally,
Can I ask,
yep.
in that sort of experimental cell, did you look at what role change in the environment could play?
Because it's just a well with only the T cells and the tumor cells, we didn't have a microenvironment or anything like that, so no.
Well, there's media, right?
Media, yeah.
So you
But we
could,
didn't change the media. Actually, changing the media kind of screws up that system a little bit. So we didn't do that. Very highly simplified system. Okay, but is cargo the right model? Is it the best model? Right? I think this is something we all ask ourselves as modelers, right? Is this the right model? Is this the best model? Okay, so well, first of all, okay, so now a data first approach. Okay, now the chicken. And enter a machine learning superhero. Okay. So this is hopefully, I think a lot of you are on Twitter, so you know what Dolly is.
Yes.
Dolly is this image generating machine learning, which you give it a text prompt and it'll give you an image. So I put in a machine learning superhero, and this is what it gave me. And again, this is the star work of Alex Brummer, which is currently under review, but it's sitting on bioRxiv if you wanted to look it up. Brummer et al. 2022 should get you there. So now we're to the main dish, model identification. So based on our experience with the model first approach, the dimensionality of our data, our knowledge of the system, we're looking to identify a model of this form. It doesn't have to be this form, and this is what I really like about Cindy. It's not just data. It's not just put data in the black box and get an answer. You have to put terms in the library. You have to build equations that make sense for that system, and that requires knowledge of that system and knowledge of what it is you're looking for, okay? So, for example, what we're going to do is still look at a two-dimensional system, X and Y, but now have terms that are growth or death, binding of the CAR T cell and tumor cells, and we're going to call functional response. So how does that actually work? How does Cindy actually work? We seek to identify a dynamical system of the form, X dot equals some function of X and T, not X and T, but X of T, via a sparse regression in the function space, okay, by solving this linear system of equations that I described earlier, where X is a vector of data, theta is a library of terms, and C is the coefficients of terms in the model. And we optimize the following quantity, okay? This quantity here, which is our cost function quantity that we're optimizing, has model data agreement here, first term. This is a regularization term, which in our case is an L1 regularization, if anybody's interested. And what it does is it prunes off small terms. It keeps the big terms and then prunes off the small terms. And then this is a model fit term. And those three combine together to converge to, let's see, what kind of stuff. In this particular case, we use this beautiful package, PyCindy, which is developed and maintained by Steve Brunton and Coots, which, go bananas with it. It's really great. Okay, but wait. I'm sorry, Kim, to put you on the spot, but I think about you a lot whenever I think about immunology. Well, but wait, what about the non-adherent CAR T cells? Didn't I say at the beginning that the T cells weren't adhering to the bottom of the plate? Yes, that's true. We don't actually observe the CAR T cells directly. Okay, they don't adhere to the bottom of the plate. They don't change the impedance. There's no signal from the CAR T cells. Okay, but we know how much we put in, and we count them at the end. So we at least have what we call in math terms a boundary value problem. We at least know these 2 points, okay? So we have to figure out what's in between. And now comes another cool thing that if you aren't immediately familiar with Tockin's theorem, I hope that now you have a newfound love of it or start to think about it, is a theorem from 1981 about information encoding in coupled dynamical systems. And so you can take, for example, the Lorentz system. And if you took just one of the variables in the Lorentz system, X, over time, what you can do is you can reconstruct, again, with sufficient data, but I'm showing you, in this particular case, we actually have sufficient data. With sufficiently dense data, what you can do is what's called a time delay embedding, and you can start to reconstruct the other variables in the system with having no information about them. And if that also doesn't just completely blow your mind, I don't know what will, or maybe you're not listening. That's something that is absolutely insane to think about, okay? Really insane to think about. It's a way of constructing what you call these shadow manifolds of other variables in the dynamical system. And if you remember what our data looks like, it is very highly densely sampled in time. So this is something that we can do. And we do it to identify what the CAR T cell dynamics are. So latent variable identification is seeking the dynamics of the CAR T cells, which we don't know, but we know their initial and final points, through a minimization of the mutual information shared over the time series between any two time points, and a minimization, if you will, or identification of an optimal number of embedding dimensions. So you can, in theory, if you have really infinitely resolved data, you could embed, in theory, infinitely many times, but particularly in this system, there's only two players in this system, the tumor cells and the T cells, right? Because it's just a little well. And it turns out that when you do a kind of nearest neighbor kind of analysis, you do in fact find that there's really just two dimensions in this system. So we're going to time delay embed to figure out what the dynamics of the CAR T cells are, and really that's all that's there, okay? And that's how we get the Y terms in our Cindy regression, which are the CAR T cells. So then what do we put in the library? Well, again, this is something that becomes kind of back to what we're all familiar with, which is a little bit of an art. What do we put in there? Stuff that we think should be in there from biological point of view. So for growth and death terms, you could think about exponential, but I don't need to explain to you exponential. I also don't need to explain logistic growth, but logistic growth is an option. A weakly effect is an option where there's kind of a critical damping parameter, but it has kind of a characteristically different shape than logistic growth and it saturates. Or a strongly effect where there's actually a critical threshold below which the tumor cells can't proliferate or become confluent in the well or whatever, right? So these are the three terms that we chose to put in there. One thing that I realized this morning actually in my extremely tired state was that I didn't explain one step in here, and that is that we multiply all these terms out to get polynomials. So if you multiply this out, you get x minus x squared. This is like an x cubed, and this is also an x cubed with different kind of signs. And then so what we do is put terms in the library that are polynomial shape that are going to simplify to this. Okay. And also I didn't mention it here, but I'll say it. Okay, so then what about CAR T cell functional response? So how do the CAR T cells change their behavior depending on based on the cancer cell behavior? You can have a type 1 response, which is always fast, a type 2 response, which is fast to slow, or a type 3. And you should recognize these as, first and second order kind of hill-like functions that are very always classically used in ecology. The thing I didn't write down right here, which was Alex's very brilliant idea, was to do Taylor approximations of these rational functions. And then that's how he starts to figure out what these terms look like by regrouping. And then the other thing we were thinking about, although I didn't talk about today just for time, was there is an interesting dynamic that can play out depending on how many CAR T cells bind to an individual tumor cell. So we wanted to put also in the model library, in the term library, what happens under different kind of binding dynamics. Is it 1-to-1? Is it many to 1? Is it 2-to-1? And you can write down what all these kinds of conditions are, like what happens when there are many different kinds of bindings, and you get different kind of functional binding forms, which again, we do this kind of Taylor expansion to approximate. So going to Sandy's question, and I'm sure something that was on all of your minds here is, okay, well, but it's probably going to find a class of equivalent models. And yes, that's definitely true. Okay, so remember in the cost function, there was a regularization term that has a hyperparameter with it, lambda. And what you can do is you can just, you do regression under a number of different terms, and you identify the model as the most parsimonious. So minimizes the error between the model and data, and also has the fewest number of terms, okay? And also has something to do with sparsity. So what you're looking at here in each column is different tumor to CAR T cell ratios, and the black circle indicates which model was selected. And the model selection really comes down to this Pareto front on the bottom, where you're looking on the y-axis at the root mean square error in the data, and then on the x-axis here clearly is the number of terms. And so you're kind of trying to balance these things out. So this leads to a very important point. Does Cindy give you the answer? Well, if you don't already know what it is, not uniquely, no. Okay, so there are many equivalent functions, but part of what I really love about this is we all know that. From our research, from the workshop, we all know that you can fit 15 different models to your handful of data that you have. We all know that, okay? Is there any beautiful truth that anyone has given us to say this is the model? No, not really. But what's nice about this is it's a very specific algorithm, a very specific concrete way to determine under a rule of parsimony what model would be the best in your candidate library. Okay.
I know this is very trivial. I'm sure you did it. You separate the data into training and validation, or?
Training and validation. So no, in this paper, what we did is we were focused mostly on the method. So we did it on all the data. We didn't then ask the question, does that identified model then fit another data that wasn't trained on? We didn't do that in this paper because we were focused on just working out all the method. But it's a natural question to ask, yeah. So what are the results? What are the discovered models? What do we find?
Can I just ask, talk about best model? That's a loaded term. And so I just want to know is, like, how do you define that? What for you is it
The one that minimizes the error and the number of terms, both.
So it's about minimal and accuracy.
Yep.
But that isn't necessarily the most interpretable or understandable or insightful.
True. That is true. However, part of the beauty of Cindy is, like I said, it works. What I mean, it works. It works.
It might not be testable.
Well, this again comes down to your data, your question, and the models. If you put junk in there, then it could be interpretable junk, both on the data side and on the model side. But if you have a very specific question, very specific model terms, and a very specific kind of data to answer that question, then you can construct it such that it is interpretable.
So do you guys use the Kaike information criteria to determine which model?
Yes, we did.
Yeah, okay.
We used AIC and BIC, and Alex can tell me what the other one was.
A bunch of them. It doesn't really matter. The thing is, like,
But
there's a standard for this.
but then we compare them from an Kaike criterion kind of perspective, where it's like, okay, what's that balance between model fit and parameters?
Mhm.
Yeah. So what are some of the models that we discovered?
We have a question from Gary Ann from Vermont. Do the different, let me see if I can read it here. Do the different sufficient models represent different testable hypotheses?
Yes,
I guess they do, right?
that's what this slide
If
is.
they're different.
That's what this slide is. Yeah. That's this slide. So what did we discover with this approach? Okay. Again, I'm skipping over a lot of the details because I said I wanted to focus on what I thought was the most interesting part, which is the concept of model first versus data first and the math. I could have given an equally long discussion about the different tumor lines we use, the different CAR T-cell lines we use, the different ratios. There's a lot of depth here, but I'm focusing on a specific level.
It's okay, you're there on Sunday, right?
Yeah, exactly, right, yeah.
It's fine.
Yeah, you guys don't have dinner plans, right? So for example, for this particular cell line and this E to T ratio, it identifies a weak allele effect in the tumor cells and a double binding and a logistic growth in the T cells and a type 2 expansion in the T cells. That is something that you can validate because you can do a binding assay. You can do a CAR T-cell alone or in co-culture expansion assay.
Is your variable here of the unit cell index?
Yes. Yep. So very good question, Heiko. So like I showed before, the correlation between cell index and cell number is like 95. So we just map back and forth whenever we need to, but the model works in cell index space. That's a very good point. And so for that reason, those dimensions have to be mapped back if you want to do something meaningful like that. And then at a different E to T ratio, we have, again, a weak allele, but single binding, logistic and type 2 expansion. So all of a sudden, immediately now, you have this hypothesis that at different E to T ratios, you can expect different CAR T-cell effector to target bindings. And that's important. Why is that important? Because it depends on, for example, that may affect how different antigen densities are going to be effective or not, if they're having more T cells bound or not. If you're going to design a CAR T cell with multiple receptors, is your, the dimensionality of your target space going to be reduced because CAR T cells are more bound or less bound to their targets? And then yet another lower E:T ratio, you have now logistic tumor growth, single binding, type 3 expansion, and double binding. So these are all very specific concrete hypotheses that we are actually actively doing experiments to validate. I don't have to show you right now, but yes, they are being validated.
So Russ,
yeah,
it's incredibly beautiful, right? It is. So what you can see here is that your growth rate and your carrying capacities are quite different between your different initial conditions of effect on T cells. Is it possible to do a dual fit to just these data, to fit simultaneously to these kind of data, that you arrive at a global growth rate and a global carrying capacity?
That is a very good question, Heiko, because this is the discussion I literally had with Martina postdoc yesterday afternoon before I left for the airport. That is exactly what we talked about. And
did you decide to do it? We had the discussion.
To ask her. She gets off the plane in like an hour. Ask her what she did on the flight. Yeah, I don't know. We asked. I don't know, but we actually asked that exact question of what happened. Would it be different if you do that? Yeah.
Because then it comes down to identifiability again, right?
Yeah, it does. Yeah, there's a trade-off there, but yeah, we do actually interestingly talked about that. Yeah.
I have a question. So on the right two panels, it looks like there's like I'm curious if so you're giving your input of function space. You're defining what your function space is. I'm wondering, given these two panels on the right, I'm wondering if could you maybe be missing something, because there's some, like in the middle, you see this little dip.
Yeah.
But it looks like your function space is not able to capture that.
So there is a perfect. Okay, so
like,
good question, Daniel.
Like you're getting like some like false positive.
Yeah, so good question, Daniel. So I mean, this goes to what we all know is the fundamental issue of like, could you add more terms and more parameters and fit it better?
Yeah.
Yes, you could, but it wouldn't satisfy this parsimony requirement.
Yeah.
So that you'd have to be going out, you'd have to be increasing the terms and then therefore changing the structure of the model.
Well, I'm wondering.
This actually goes to Sandy's point too, of like, if you start to expand out too much, what does a sixth order term even mean in this system? You could add it and it would probably fit it better, but it may not be interpretable.
Yeah, but I'm wondering if rather than if there's some functional form that can replace all the, it's not an added term, but it's a, you know what I mean? Like it's like a different.
So
term.
in the structure of the discovered models that we're looking for, there, like you could, but this is part of what I'm saying. What I like about Cindy so much is like we're looking for something of this form because we're wanting to answer that kind of question. If you want to put higher order terms in there that are either interpretable or not, or have a meaning to you or not, and you're willing to go past the identifiability issue and go past this double descent of say, okay, let's just overfit it to crazy levels and see what happens, you could do that.
Yeah.
You could do that.
Okay.
We haven't, but you could.
Yeah, no, okay.
If you do it, tell me what you'd find. All this data is attached to the paper, by the way. So you can run it all. All the data and code is attached to the paper, so you can run it all yourself and change it.
If you're missing like a fundamental variable, right? So you've got two variables there, but say there's a third that you're not measuring, but it's actually really crucial in this. You can try and capture it through the interaction terms and your other variables, but it's not there.
You could, but I think this is what we effectively argue, and I will argue, is that there's actually really only two dimensions to this system, mathematically and biologically. It's a well, and with tumor cells and T cells, there's nothing else in there.
Well, they could be secreting something, right?
Yeah, and there could be oxygen and stuff like that. But I mean, there's really two players in this two-dimensional system, right? So, yeah. Okay, so what's the upshot of this? Here's the cargo model. Here's the Cindy model, just for comparison. And what's important to notice, and this I guess goes to Daniel's question too, what's important to notice is that they have very similar model fits. Not perfectly identical, but they both fit the data. The tumor, the excelligence data. Where they differ is in the predicted N CAR T cell.
Big difference.
So actually, Cindy directly hits the final T cell population, whereas the cargo model doesn't. So the blue curve, which is cargo, doesn't hit this black dot, which is the final endpoint, whereas the red ones do. And that is a very interesting difference because remember, we didn't directly observe the CAR T cells. Those data points are real, they're measured, but the trajectories in between, we don't know. That's the talk concern, that's the dimensional embedding stuff. And that is one thing that, like I said, part of what I find so fascinating, what I love so much about this area right now of research that I'm talking about today, is it addresses all this hard stuff we know, okay? Who knows if it's the right model? Who knows if it's the correct model? Who knows if it's the exact right model? Who knows if it has all the right terms, all the right variables? You don't know, okay? You can always fit the data. Anybody can fit the data with anything.
Yeah.
Can we do it in a way that teaches us something, that asks a question, that we learn something from, that hybridizes data first and model? That's where I think this is all going. That's what I get excited about.
Why was the cargo model not able to fit the last data point? Was it not included in the fitting function?
So that is a very good question. Could some other parameter combination have fit it? Possibly. But what happened, like we do whenever we do model fits, right, is we're basically doing like a Levenberg-Marquardt local search, right? And it just didn't converge to that. Now, one other thing that we've done that's of interest is done like particle swarm optimization to look for global solutions, try to get to a global minima and then do Levenberg locally. But we didn't do that here. That's what I'm saying. That's more recent than what this data was.
But you would agree that there is a non-zero probability that the cargo model could fit equally well.
That you could have fit it equally well. Right, exactly. Yeah.
So going the other way, Cindy, did you input the CAR T cell data for Cindy, or is this what you get out?
So what we put into Cindy was the latent variable reconstruction. So we went through and did the latent variable reconstruction of Y based on the endpoints.
Okay, so you did have the endpoints.
So you have X and you have the endpoints of Y. You do the embedding. You choose it such that it fits the endpoints, the boundary value problem.
Okay.
And that identified trajectory, which is not directly observed, is what goes in here.
Okay.
So first of all, I am a very huge fan of Takan's Theorem, shadow manifolds. I did my master thesis on that, and I am super happy to see that somebody else is doing it.
Okay.
However, one thing that I was trying to do and that did not work very well was, applicability of the whole stuff on a very nicely synchronized oscillatory system. And something I've learned is that, you need to have perturbations to actually figure out if there's anything missing. And I'm looking at your model, I'm looking at your intuition, and it's like, yes, we do capture behavior of the system. We kind of guess the interactions. We can have a nice grasp of what is going on. But I'm wondering if we have more variables that could potentially affect the system, if there are any synchronizations, if you could cut it off and see if your model is still behaving correctly, but what will change?
Yeah, that is a very good question, and I don't know. Sounds like since you did your thesis on it, you probably know a lot more about it than I do. But I can tell you that part of the idea here is that it is a very highly simplified system where we can have a pretty good sense that it's like, okay, fine, that trajectory is probably what's actually happening because the CAR T cells aren't like multiplying tenfold or anything over like 3 days, right? I mean, they're probably basically just going up a little bit and staying steady.
Mm-hmm. So there was were there any experiments done where you're like just take some of the data points out and see if the whole thing will be still working if you have missing data points?
You mean just in general data density in Cindy, or are you talking, what do you mean?
So I'm actually talking two things. So here, for instance, if you remove the data points between 50 and 80, will you still get the same equations?
We haven't studied that. That's a very good question.
Okay, cool. Thank you.
Because this is very early days in all of this, okay? Very, very early days. So in fact, part of the reason why I don't have the validation experiments for you is because we wanted it published. Because to my knowledge, this is the first application of Cindy to biological data. So I wanted to get that out. But I think there's a whole career to study here, to be totally honest. I mean, you can spend your entire career here. So in summary, the model first approach, as we all know, has a lot of value. And so we used it to study CAR T-cell and cancer cell dynamics and the effects of dexamethasone, which has these kind of unintuitive nonlinear effects on both populations. But yeah, this is the first, to our knowledge, implementation of Cindy on biological data. And I think we have the possibility of getting to the point where we can discover the equations of biology. I really do. Maybe not this year, maybe not next year, but we're going to get to the point where we have enough data, enough dense data, where we can start to make those kinds of claims with this kind of approach. And then we have to interpret the discovered models. So look, depending on E:T ratios, what kind of CAR T-cell expansion dynamics are you expecting? What kind of target to effector binding dynamics are you expecting? And those are things that you can experimentally validate. And if they work, they work. If they don't, then you're in the list with everybody else in the world of, an idea that didn't work out. So which comes first? It's a trick question. I was really hoping to put a turkey here, but I couldn't find it. The turkey with the egg. It's a trick question. Okay. So, and then here's the final thought here. The impressionist painting of a machine learning biology from Dolly, which I actually really liked. I've been playing around with Dolly quite a bit. This one I actually genuinely liked. Okay. So thank you, everybody. And I look forward to a lot of nice discussion on this, or adversarial discussion is fine too.
Cool. Yes, I mean, technically, you're supposed to go to the meeting at 2, which is great. But if anyone has questions, that's a good time.
Extremely cool stuff. But I'm kind of puzzled that it went so well from like in vitro to in vivo, because there you don't have just 2 players. You have all this kind of suppressive T cells, macrophages. You have complex spatial structure. So what's your why do you think it was translatable?
Why do I think it will be?
Well, no. I'm thinking
I
like
didn't
you
translate. I didn't show Cindy in vivo, only in vitro.
No. I'm not talking about Cindy. So I'm talking about sort of. I think when you went to analyze that patient data. It seemed to be kind of a very good fit with.
Yeah, but that was. I mean, that's just the same thing that any number of people in this room do on a daily basis. Just fit a model to data. There's nothing special about it. It's just a simple model with few parameters that you could. If you see here, each column here is a time point, and each row is a lesion. So there's 1, 2, 3, 4, 5, 6 time points. You can fit a model with 3 parameters to 6 time points reasonably. It works.
So my question goes in the same direction about requirement of longitudinal clinical data to use these kind of approaches to get to identify models and maybe really identify whether another mechanistic term is required or if another key player is required, right? How can does this give us a new tool? And I hope it does, that offers us whether a player is missing or just another mechanism of existing players is not considered. Do you think that will be doable with this approach to compare a 2 or 3 player strategy versus a 2-player strategy with higher complexity?
That's a really good question, Aiko. I don't have a great answer for it, but I'll say 2 things, okay? One is that this is extremely fast. running Cindy on this stuff is like on your laptop in a minute, okay? Very computationally light. So you could explore a number of scenarios, look at the models, look at the terms, study it, and see. That's one like pretty bootstrapping answer of like, I don't know, just look at a lot of options and see.
Do manual perturbations of the above and then do an AIC on whatever comes out of that.
That's one answer, but the other answer is that, once you start down this path of Cindy, I mean, there is a really surprising amount of papers that have been published on it in the last couple of years. Most of them are still on arXiv and bioRxiv, but I think the advancement in the methodology is moving so fast that I wouldn't be surprised at all if someone came up with a way to specifically address that. That's not an area of research that we're actively doing right now, but part of what I'm saying is that like it's not hard to imagine a future where there's both a huge density of data and let's say the right kind of data or the data that you want to study to tell you something where this could work. I say it's not today, but it's probably not that far into the future. Going back to what we started this talk with, about the first time I came here in 2006 when Sandy was in a closet. His office was a closet. How much has changed since then, right? That's what I'm thinking.
It's absolutely beautiful.
But I think there probably would be a way methodologically to do it. And a lot of the advances, one of your other first questions was about noisy data. There are flavors of Cindy, and Ryan's really the expert on a lot of this stuff. So if you want to get into a lot of the details, Ryan's the one who's read most of the papers on it. For example, noisy data, structured data, spatial data, all these variations have been addressed. But so far, there's hardly any application to real data. So all the papers you'll find on Cindy, except ours, arguably, will be on, run a model forward and see what happens. There's one very notable exception, and I'll just say because I want to. They got the Brunton and Coots, who are really leading all of this. Their main interest is climate change. They want to use this for global weather patterns. And in fact, we saw a beautiful talk earlier this year from faculty at Oxford. I don't remember her name, where she actually discovered new physics at what she called a meso interaction scale in between land and sea that was not obeying, let's say, classical turbulent flow kind of dynamics that might have some kind of climate-based implication. But that was data-driven. That wasn't modeling. That was like, Cindy on climate data. So, we're challenged in cancer by the, how often you can get data and all this stuff, but it's easy to imagine ways in which you can overcome that barrier eventually.
Okay, well, thank you very much once again.
Question about the cold dimension.
This is faster than
Yes, you do.
I do, well,
Okay, I take that.
I do think about you a lot when I think about CAR T cells.
So,